All right, so we had some people asking about more proofs by induction, so I just wanted to give a couple more examples. Looking here at number 7, proving that 2 to the n is greater than n for n greater than or equal to 1. Means our base case is n equals 1. So we look at what 2 to the 1 equals. That equals 2. And 2 is bigger than 1. So we have our base case. We use our induction hypothesis right up here. So we assume let 2 to the n be bigger than n, and then we consider 2 to the n plus 1, which is equal to 2 times 2 to the n, which is strictly greater than 2 times n by our induction hypothesis. 2 times n is the same as n plus n, and n plus n is greater than or equal to n plus 1 because n is greater than or equal to 1. And that's our proof by induction. We proved that the 2 to the n plus 1 is greater than n plus 1. So we proved it for all values of n. Okay. A little bit trickier on question 8. Oops. Let's go to the pen. There we go. Question 8 has a little star next to it. This one's a little trickier. If I write 4 to the n, I'll just abbreviate here. If we go to the base case, 4 to the 1 is 4, and 4 is greater than 1, which is equal to 1 squared. So we proved it for the base case. And then we assume that 4 to the n is greater than n squared. So then we look at the n plus 1th value. Consider 4 raised to the n plus 1. Unfortunately, what we just tried on the last one doesn't get us very far. If we do 4 times 4 to the n, we can say, well, that's greater than 4 times n squared. But it's not entirely clear how to turn this into, so I'll just draw like an arrow with a question mark. How do I turn this into n plus 1 squared? It's a little bit confusing. So there might be might be some way to do this. There should be some way to do this. It feels like it should be true that 4 times n squared should be bigger than n plus 1 squared. Over here on the side, we can do n plus 1 squared is n squared plus 2n plus 1. So maybe we can break up our 4n squared into pieces and see if we can prove, that each of those pieces is going to be bigger. Yeah, that might work. So 4n squared is the same as n squared plus 2n squared plus n squared. And this piece right here is equal to n squared, obviously. This piece right here is greater than or equal to 2n. And this piece right here is greater than or equal to 1. And why am I allowed to do that? Because n is greater than or equal to 1. And so n squared is going to be greater than or equal to n, because you're multiplying by numbers that are at least 1. And n squared is going to be greater than 1, because you're multiplying by numbers that are greater than or equal to 1. And so this right here is n plus 1 squared. So that's a little trickier of a proof, but it also seems to work out. Okay, so those were some ones with inequalities. Maybe it's overkill, but I'll try number 10. So we have 1 plus a, and we're looking at n is greater than 1, n is greater than or equal to 1. So we have 1 plus a to the first power, which just equals 1 plus a, and that's the same as 1 plus 1a, so we have a base case. Base case. Now let's look at the n plus 1th case. 1 plus a to the n plus 1 is equal to 1 plus a times 1 plus a to the n. I guess I'm going to use the induction hypothesis here. What does that give me? That gives me 1 plus a times 1 plus na. And we know this is greater than or equal to by the induction hypothesis. And we're trying to get to, I'm kind of losing track of stuff here. We're trying to get to 1 plus n plus 1a. In other words, 1 plus na plus a. Let's see what happens if we multiply out what we have. Boop, boop. So we have 1 plus na plus a plus na squared. What do we know about a? A is greater than negative 1. What do we know here? Let's see. So we have this piece, we have this piece, we have this piece. We just need to prove then basically the last piece of the puzzle just needs to be greater than 0. And that's true because the a value is squared and the n is a positive integer. And so we can say here that this is strictly greater than 1 plus na plus a, which is 1 plus n plus 1a. So there you go. A couple more induction examples for your viewing pleasure. Comment or ask questions if there's anything I can do to help.